all the kind of the basic rules about inverses and stuff like that, but it also has the majority of the graphing. And what I usually do is I break the chapter up and quiz after we get through all the graphing portion. Just right here. Thanks. Good luck. And what I'm thinking about doing is we'll probably quiz over the first three, maybe Thursday. 9.2 usually doesn't take very long to get through. 9.3 usually takes an extra day. It's usually about a day and a half, to be honest with you, just to make sure you guys understand a lot of it. But the other thing is that with this graph that we're going to be working on here, a lot of it is non-calculated, so you know. Because there's a process to which how we set these things up with these rational functions. And today you'll see the basics of it, and you'll recognize it doesn't change as the polynomials and stuff start to get a little bit more complex. It's still kind of the same process. So, graphing simple rational functions. Well, rational functions are just polynomial divided by polynomial. Is really what we're looking at here today. Polynomial divided by a polynomial. And most of our things that we're going to look at today are going to look like hyperbolas. When we did hyperbolas in the conic stuff, our hyperbolas were either left and right or up and down. Here we're going to wind up with hyperbolas that will be kind of diagonal off of one another. Okay? Put off. They'll be more off the sides. They're going to be blocked out by different types of asymptotes as opposed to what we had earlier. Yeah. So, first one we're going to look at is kind of the most basic rational function. Y equals 1 over x. And I want to walk you through how we graph y equals 1 over x. And this is kind of the same idea. In this case here, what can't the denominator do? 0. So if 0 can't be in the denominator, bless you, what is created when you graph it? Very good, an asymptote. You have a vertical asymptote. Whatever. Will always be at the 0 of the denominator. Okay? Your vertical asymptotes for all rational functions will be at the 0 of the denominator because you can't divide by 0. Whether that is a polynomial where you have 2 zeros, 3 zeros, something like that, you can have vertical asymptotes in multiple spots. In this case here, I have one of them, and it is at 0. Vertical, are they x equal a number or y equals a number?
X equals 0.
Very good. So my vertical asymptote, it's going to be at x equals 0. Do you guys remember how to draw that when you have an axis and it's on the axis? You could do this and kind of overdo it if you want, but a lot of times people would do this and just write dotted because it's an asymptote. Does that make sense? Remember when we did that with graphs sometimes when we had the parabolas where they were solid or dotted, depending on if it's less than or equal to or greater than or that kind of junk? It's the same idea. If you have an asymptote on an axis, you can go ahead and just put it as a put a line to it and just say dotted. I'll be okay. Because you'll start listing them out as far as domains and stuff. Excuse me. Next little bit we're going to look at is, let's make a table. The next thing you guys would normally do is make a table. You pick some numbers. It makes no difference as far as what numbers you pick. But I want you guys to see, we're going to start picking numbers that are on both sides of our vertical asymptotes. So if I pick -2, -1, 1 and 2. At -2, I substitute in, I get what? -1/2. -1. 0 we know is undefined. 1 and 1/2 again. Everybody okay with those? They match out pretty quick. Yes, ma'am.
Why is it undefined?
Can you divide by 0?
Okay, yeah, but like, so that's what it is. When
Yeah.
you can't, when you're dividing by 0, it's known as undefined.
Correct, because that's where our asymptote is. Now, if it was this, where would your asymptote be at? Ooh, you have 1. So then at 1, it would be undefined.
Wait, homie.
Oh, because then it'd be one
Oh,
over
homie.
0.
Wait, hold on,
Okay, that
hold on,
makes
wait.
sense.
So x minus 1 equals 0.
Oh.
I just moved the asymptote.
Makes sense now.
Okay. So
Yeah.
we knew then at -2, at -2 is at a half. At -1, it's -1. 1, 1, 1.
Oh.
What happens if I pick 1/2, just for fun? If I pick 1/2, or 1/3, let's try it that way. If I substitute in x is 1/3, I get 1 divided by 1/3. What do you get? So when you divide by a fraction, you multiply by its. So what's 1 divided by 1/3 is 3. If it's oh, I just didn't hear you. Sorry. Same idea. So what's happening here? Oops. What's happening is we're getting this curve. Will I ever reach 0 on the x-axis? Yeah, because no matter what, I can get closer and closer and closer to y equaling 0, but I'm never going to get there, am I? No. So I wind up with an asymptote also in this case at y equals 0.
Yay.
There's a horizontal asymptote at y equals 0. Mr. Pope, they're towing your car. I don't know. All right. So that's the idea of what we're starting to look at here. I want you guys just to get the feel for picking numbers, identifying asymptotes, and going for it. Now, if I'm going to ask you what's your domain, is that your x values or your y values? Oh, what comes first in the alphabet? Domain or range?
Domain.
Okay. Doe is a deer. It's a female deer. Sorry.
Ray.
It's a drop of golden sun. I'm sorry. Yes, ma'am. Asymptote. Asymptote is a value that you're approaching, but you're never going to get there. It's like this. I'm not touching you. 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 Can you infinitely get closer to something without ever getting to it?
Yes, because
Can you always take
geometry
half
is-
of a number? That's the idea. Yes, sir.
We did this kind of thing, like the whole like getting closer and closer and closer thing in geometry, because my friend came up with a theorem where since a point is infinitely small and a line is made between two points and is infinitely thin, then a plane is made of lines. So it's like,
Plane is not made of lines. Plane is made of non-collinear points.
You're right. But then a plane is infinitely small. And doesn't
Or a plane can be infinitely large.
Yeah. But then the idea is that you write infinitely small as 0.01 or 0.0 repeating and then 1 and then it doesn't exist and you can't do that. So we broke math.
Yeah, anyway. Basically what we're looking at here is, as we go through these things here, you've got your domain and ranges. I forgot to list those out, sorry. Your domain here is all values of x not equal to, getting ahead of myself. X not equal to 0. Our range is going to be all values of y not equal to 0 as well. There will be eventually a different way that we'll write out domains and ranges in terms of what's called set notation. It's kind of fancy. It just looks like you're smart. Strive for good. But let's look at it in terms of what happens when we move stuff around. let's put a rational function in terms of a, h, and k. Let's look at rational functions. We're going to look at them in two ways today. A, h, and k, and then another somewhat similar to one. So if y equals a over x minus h plus k. What we've done here is taken the value of 1 over x, where a was 1 and h and k were both zeros, is that we're putting right at it, when we're shifting it and putting a scalar in there. A is going to be a scalar for us. H and k move us horizontally or vertically. I know there's no k in vertical. I know you looked up, and spell it in your head. What happens here is you will always, always, always have a horizontal asymptote at y equals k. You will always have a vertical asymptote at x equals h. When we start to plot these things, that's the very first thing you're always going to plot, are your horizontal and your vertical asymptotes. Which means, when you're looking at an equation, you want to identify a, h, and k right away. Basically, every graph that we do from here on out is going to have some a, h, and k component, whether it's these rationals, radicals, next chapter, logarithmic, exponentials, trigonometric. Every one of them is going to have some sort of a, h, and k component to it. And they all kind of stand for the same thing. A is a scalar, how fast something's increasing or decreasing. H is always be a horizontal shift. K is always a vertical shift. It allows you to identify domain and range rather quickly. All right? So if I have, yes ma'am?
So that is the formula for graphing?
Yes.
Okay.
Yeah. This is going to be our generic way of doing it. All right?
Okay.
So if I start right off the bat with y equals negative 2 over x plus 3 all minus 1, I'm going to always start with a, h, and k. What are they? So what's a? Negative 2. What's h? Negative 3. Very good. What's k? Negative 1. Good. So our a value, negative 2. H value was negative 3. K was negative 1. Which tells you right off the bat, without having to do anything, you have a vertical asymptote at x equals negative 3. Notice the vertical asymptote is the 0 of the denominator. Okay? Of course, it's crazy, isn't it? Our horizontal asymptote is at our k value, y equals negative 1. Come on, guys. So we plot it. We put in our axis, Mr. Pope. Come on. Talk to her later. We put in our asymptotes. They were at negative 3 and negative 1. We know that right away. What we don't know is what the curves are doing. So we need to pick points. And we're going to do this stuff as a mental exercise. This is great. What I want you guys to think of here is that we need to know what's happening on both sides of the vertical asymptote. So we're going to check 2 points on one side and 2 points on the other. 2 points on the left, well, I got negative 4 and negative 5. And then on the right, we have what, negative 2 and negative 1. And we're just going to substitute in the value of x and work through it. Okay? So, what's negative 4 plus 3? What's negative 2 divided by negative 1? 2. What's 2 minus 1? 1. So at negative 4, we're at 1. Do the same thing with negative 5. What's negative 5 plus 3? Negative 2. What's negative 2 divided by negative 2? 1. What's 1 minus 1? 0. Do I have enough points on that portion to tell what direction that curve is going? One's lower than the other. They're approaching asymptotes both directions. So our curve is doing this. And now I substitute in on the exact same values for the other side. Okay. What's negative? Yes, ma'am.
How did you find the
Vertical asymptote's always at 0 denominator. Horizontal asymptote's always the k value.
Oh.
It's the h and k. The h and k. -2. What's -2 plus 3? 1. What's -2 divided by 1? -2. What's negative? I said 1. What's -2 minus 1? So at -2, 1, 2, 3. I'm at -3. I do the same thing with -1. -1 plus 3. 2. I know it's tough. It's been a long day. -2 divided by 2 is -1. -1 minus 1 is -2. And I have 2 points. You'll notice it's moving this direction. What's your domain? What can't x be?
0.
No, x can do 0. It goes through the
X
axis.
can be -3.
-3, so that means my domain is all real. X not equal to -3. My range, where's my horizontal asymptote? At -1. The range is all real. Y not equal to -1.
So it's just your asymptotes.
Yes, sir. Your asymptotes are your domain range restrictions.
Just need to find 2 points or 1 point. Because you already know it's going to curve up against the edge.
Ah, but what direction? I mean, yeah, I see what you're saying, but I want 2.
Oh, okay.
Yes, ma'am. Same thing.
So is your domain range always like
If you know your H and K, yes. Yeah, and that's what's nice about rationals. It's really pretty quick to set up the domains. Yes, ma'am.
Did you just pick out like random numbers for the
Yeah, I can pick any number I want. I'm just picking the next 2 because it's the closest to the asymptotes and usually works out to be the cleanest.
So the closest to the x.
Yeah, it's fine. It's your best bet. You could have picked 1 and 5 if you wanted, but it's not going to show you much of a curve. It's going to be tough because you'll have more of a fractional value. When you're closer to the asymptote, you're probably going to be at the greater change of direction, so you might see a bigger variance between the 2 values, so you might see how fast the curve is changing. That's the only reason why we choose the next 2, because you're going to get the biggest variance.
So how did you find the y?
I just substituted
Or where?
the given equation.
Yeah.
Yes.
Okay.
Chuck, but you have to do it mentally. Correct. Start over. Let's look at the other version of it. The other form that we're going to look at today is very similar except that it has 2 variables, or 2 values of x, I should say. Oops. We have ax plus b and cx plus d. What I want you guys to look at is, as far as how this setup is, think of it as noticing that you have the same degree in both the numerator and the denominator. Both the numerator is a linear function, and same as the denominator is a linear function. They both have a degree of 1. Whereas when we did this one, we had a constant up top and the variable below. Okay? Here we're going to have 2 variables same degree. They're both linear. When you have that happening, you're going to be able to figure out a couple of things. Since the degree here for both the top and the bottom are the same, you have a horizontal asymptote at the leading term's coefficients. Okay. Your horizontal asymptote will be at y equals a over c. Leading term coefficient. And I'll walk you through an example here in a second. Your vertical asymptote never changes. It's always the zero of the denominator. That never changes. The zero of the denominator will always give you your vertical asymptote. Your horizontal asymptote in this case is just be a leading term coefficients. What's nice about this is that if you recognize any rational function that we work with, whether it's today or the stuff we do tomorrow, if the degrees are the same, top and bottom, you will always have the horizontal asymptote at the leading term coefficient. There's going to be other rules tomorrow when we have different degrees, top and bottom. But for tomorrow, or for today, and tomorrow, when they're the same degree, you'll always have the asymptote at the coefficients. All right. Yes, ma'am.
So, if the leading coefficient is a whole square, then, but if they were the same.
There's other things we'll have to go over tomorrow.
Yeah. But if they were both 2, then would it be 1?
Yeah.
So would it be 2?
It's the fraction, whatever it is. If it's like 3 over 6, it's 1/2. It's things like that. It's a simplified fraction. Okay.
So it's not the leading term coefficient, then over
Yeah, it's a leading term coefficients is what I should say, like the coefficients fraction. Okay. Does that make more sense? Let me show you an example. If we do y equals 2x minus 1 over 3x plus 2. Very good. In this case here, I have degrees that are exactly the same. Both the numerator and denominator are polynomials with degree of 1. Both linear. Bless you. They're both linear. Since the degrees are the same, my horizontal asymptote is going to be at y equals 2/3. Where's my vertical asymptote? Negative 2/3. Okay. So there's my asymptotes. Well, if I pick numbers to the right, numbers to the left, probably going to pick 0, 1, -1, -2, or -2 and -3 maybe might be a little bit easier in the way it's not right next to the asymptote. You just need to have 4 points. And yeah, you will get funky fractions. So if I use 0, I get you get 2 times 0 minus 1 over 3 times 0 plus 2. You get -1/2. Okay. And I do it again. 2 times 1 minus 1 over 3 times 1 plus 2. 2 minus 1 is 1. 3 plus 2 is 5. So yeah, you will get weird fractions, but you're doing the math. Placement allows you to see the direction of the curve. 0.5, 1 and 1/5. So we're doing this. Plus, also, if you use 2 points, you'll notice if you get 2 points in the same quadrant that you've created, you know the right direction. But let's say you pick just one point and you use the wrong sign somewhere, you could have it flopped up here and you make reverse it. That's why using 2 points is it's a better thing, just so you get the right values. Same thing with -1. So that's what? -2 minus 1 is -3. -3 plus 2 is -1, so that is equal to 3. And then -2, so we have -4 minus 1, -6 plus 2, -5, or -4, so it's 1 1/4. That's what we get. All we're doing is just picking values on opposite sides of your vertical asymptote. And your vertical and your horizontal asymptotes are your restrictions as far as your domain and range are concerned. Mr. Williams?
When we get those numbers, for like the 0 and the -1/2, where do we get the 0 from?
Zero's to the right of the asymptote. It's the next number. That's it.
What's all?
That's it. That's all it is. Next number up. Think of that one. The asymptote got rid of something, so it picks the number to the right. 2 numbers to the right, 2 numbers to the left.
Like the vertical or the horizontal?
Vertical. Because your verticals are your domains. You're picking values in the domain to find values in the range.
Could you have done that 0?
Pick values in the range to get to the domain. Well, if you did that, then I'd have to substitute in y, like 2 for y. What value of x gives me 2 for y? Yeah. You want to solve that equation?
It's child's play.
It's a lot more work. Everything is domain driven. X generates Y. Think of that. Our function machine says you put a value of X in, it spits out a Y. Let's see. Why don't you guys do this one? Graphic, give me the domain and range, please. All right, real fast, 'cause we're running low here. Running out of time, I should say. The horizontal asymptotes be at y equals 1/2. I hope you guys got that.
Yeah.
Okay. Our vertical asymptotes can be at x equals 2.
2.
2.
Move 4 to the other side when you
Set that equal to 0, add 4 divided by 2.
Dang it!
That's how you do it.
You set the denominator equal to 0 and solve for x.
Even I knew that.
Error 5, Mr. Williams.
Dang it, I messed up again. I'm done mathing for the day.
So I'm going to pick 1 and 0. And then I'm going to pick 3 and 4. Because those are just the next numbers to the right and to the left of it. If I use 1, I get 2 over -2, which is -1. At 1, we're at -1. If I use 0, I get -1/4. So I know I'm doing this. Again, the reason why we use 2 points is just to make sure that we get both 2 points in that newish quadrant that we created. Because really all we've done here, guys, is just move the asymptotes from being x equals 0, y equals 0. It's just shifted them h, like an h and k, if you will. If I use 3, I get 4 up top. 6 minus 4 is 2, so 4 divided by 2 is? One of those. 4 plus 1 is 5. 5 over 4 is 5/4. So it's coming over here. And it's doing that. Domain, bless you. All real numbers where x is not equal to
2.
Domain, set of all x such that x does not equal 2. There's the fancy way to write it.
Nice.
Range, set of all y values such that y does not equal 1/2. You can write all real not equal to x not equal to 2, all real y not equal to 1/2. That's
so long.
such that.
Such that.
You said Andrew.
Huh? That's the fancy way to write it.
I messed up that graph 3 times, Murph Dog.
Mr.
I just
Murphy's
don't.
actually man. 3
Yes.
I don't have any erasers.
Homework wise. Oh, sorry. Homework wise, in 9-2, I think it's 5 something.
No, they lost
It's on page 543. Can I go to a clean slide? Put it up.
Yeah.
This is 9-2, page 543.
Yes.
12 through 18 evens. Wow, that looks so good. And then
Oh, it's terrible.
24 to 38 evens as well. The first grouping, all you're doing is figuring out where are your asymptotes. The second grouping, you're graphing them and labeling all that stuff out as well. I think both of you have to do domain and range. Okay?
Okay.
Did somebody leave their calculator charging for a long time? Very well.